Okay, so welcome back. We're starting with Meghal Gupta, who's going to be talking about insertion, deletion, locally decodable codes.
All right. So I guess the title of this talk is that constant query local insertion. Constant query codes do not exist for. Sorry. The title of this talk is that constant query locally decodable codes for insertions and deletions do not exist. So let me start by writing that down. Okay, so I guess to motivate this discussion a little bit. So in the theory of error correcting codes, one of the central objects that people study is locally decodable codes, right? Okay, so I guess people probably mostly know what an LDC is, but let me give a really quick review of what that concept is. So the goal of an LDC is to be a special type of error correcting code that satisfies the following property. So first, as usual, we take our code word and our message and we encode it into code word. But we also additionally want to satisfy the property that if we want to recover any single index xi, we can make some randomized queries to the code word and figure out that index, or figure out that index xi without querying the entire message. So to get xi, let's say I don't know, either with high probability or with probability, let's say greater than 1/2 plus epsilon, or 2/3 or whatever you want. So to get xi, we need to query some set of indices, let's say y1, y3, y5, and that'll get us xi with reasonable probability. Okay, so does the general definition of an LDC make sense? I'm sure people have mostly seen it before. Okay, so what is the simple? So in the study of substitution errors, LDCs are known to exist. People do a lot of research on what the best possible length of an LDC is, but it's well known that they exist. And even the simplest constructions of error correcting codes often have this local decodability property. It's actually a very natural property. So I guess if we're not looking at all at rate or efficiency, then a simple LDC that has this property is the Hadamard code. Okay, so the Hadamard code takes the message x1 ... xn and encodes it to a message of length 2 to the n. Such that every message of the code word yi is equal to x.i. So the reason that this has local decodability properties is if we want to decipher some index, let's say x2, then we take two indices I that differ only where they differ only on the second index of this string over here. And then if you subtract those two values, you'll get a guess for x sub 2. I guess I plus 2 is a little bit bad notation, but and even if there's a small number of errors in the string, substitution errors in the string, that will be okay. We'll come back to this example in a second when we discuss the concept of local decoding in the context of insertions and deletions. Okay, so the second area that we're talking about in this talk is insertion deletion errors. I know there's a reading group on it this semester, but so I know that some people here have some familiarity with insertion deletion codes, but I guess insertion deletion codes are in some sense a strictly more general version of substitution errors, like in insertion deletion errors, instead of the adversary being able to take this encoded word and flip some of the bits, they can actually get rid of some of them entirely. So like if you have a code word y1, y2, yn, you can just get rid of this entirely, and then the person receiving the code word will not know that y1 and y3 were not meant to be adjacent. They'll just receive the string. So like they're more, I guess they're more general than substitution errors, because one thing you could do with insertion deletion errors is you could delete y2 and then add like y2 prime back. So it would cost you two errors two like insertion deletion errors to accomplish the same task, but like, you can accomplish the same task. And I guess the question is, like, I mean, they are more general though, because you can't, you won't preserve the index information when you do insertion deletion errors. So in general, one question in insertion deletion errors is to figure out what you can and can't do compared to what you can do in the like typical error correcting code setting. So I guess one thing that's true in this setting, ECCs do exist. You can like generally error correct for insertions and deletions. So the question of this talk is, do LDCs exist? Or LCCs or whatever. And the answer to this question turns out to be no. Okay, so let's like look a little bit back at the Hadamard example, just to get a sense of like what the difference between these two contexts is. Okay, so in the Hadamard example, when we in the substitution setting, when we queried yi and yi plus 2, their difference was, as long as there are no corruptions in either of those two bits, their difference was equal to, or sorry, this is meant to be a 2, but their difference was equal to x sub 2. So the weird thing that happens in the deletion setting is when you query index I and index I plus 2, you don't actually get those two indices. You'll actually get them shifted by a little bit, right? So you won't actually get I or I plus 2. In fact, with like very good probability, you're most likely to get an index that was near them. And let's say you got like I and I plus 3. Then in the Hadamard code, that like really gives you no information about x2 anymore. So really the question is like, so these very algebraic constructions are not going to work in this setting, right? Because when you shift the index, you're actually getting by a little bit, you get like almost no information anymore in algebraic context. So the question is sort of boils down to like, can you do something more smooth? Like, can you do something where querying yi but getting yi plus minus a little bit will still allow you to decode the information you were trying to decode? Does that like sort of make sense? Yeah, so a little bit could really be a lot. So the question is, can you still be able to decode the information? And I guess that's like sort of some intuition as to why the answer is probably no, because it's really hard to extract information when you don't know, when the index you could actually get is really far away from the one you were trying to get, right? We're talking about 0-1 alphabet.
Is it still close for large alphabet?
I think it should be. I think this should translate to the same statement for a large alphabet, because as long as the alphabet is constant size, because if constant query codes don't exist, then like you should be able to group up the word into like blocks, the 0-1 word into blocks, as long as they're constant length. It should still make the same claim.
If you look at fill effects, what kind of errors you can have?
What kind of what?
Errors you can have. This group. Anyway.
I mean, okay, yeah, maybe this is not super worth discussing. It seems probably similar, but I'm not sure exactly. Yeah, so I guess that's some intuition why like these shouldn't exist. Like, you can really get like a very shifted index when you try to query some index I, you could really get a very shifted index. And like likely that was not going to contain information about the index you actually wanted information about. So yeah, so I guess that leads to the main statement of this talk, which is that constant query locally decodable codes for insertions and deletions in fact do not exist. So let me quickly talk a little bit about the background of what is known for, or like I guess what research has been done on this problem. So the first work in this area was by Ostrovsky and Paskin-Cherniavsky in 2015, where they showed polylog query insertion deletion codes do exist. This construction is basically combining like typical like substitution or substitution error LDCs with like a binary search on the index. So it's not super surprising that these objects exist. Another work that's worth discussing is the work of Blocki, Chang, Grigorescu, Li, Zhang, and Zhu of 2022 in, I guess this work is in ICITS 2015. And this work is FOCS 2021. And this work showed that for any constant query LDC, it has to be at least exponential in length, or like roughly at least exponential in length. So it doesn't like totally rule out their existence, but it shows that if you have constant query LDCs, they must be really long, so it rules them out for all practical purposes. And the thing we're going to discuss today is the statement that they do not exist at all. They cannot even exist at like, unreasonably long exponential lengths.
So I can ask a question. This first result, the polylog B, is that with constant rate and constant fraction of instell errors, or like what is the what is the length of the code that the supporting?
Definitely constant fraction of errors. I believe constant rate as well.
Constant rate as well. Yeah. Okay. Cool.
It's just what we know for Hamlet with a blow up of 3 again in query and the rate and distance.
Yeah, I mean, I believe it's basically like you can do a substitution code, but you can like add another log factor to be able to binary search for the index that you're looking for. Like, so it's really not that complex. It's really like basically just a substitution error with an extra log factor. Yeah. And then, yeah, so unfortunately, I don't think I can explain like the entire proof or like the main ideas as to why you can sort of beat the exponential result of this, but I'll try my best, and like hopefully, I'll be able to extract some idea on why you can do better than this, or at the very least, hopefully, I can explain why exponential ones aren't possible. Okay. So I guess for the rest of this talk, we're only going to focus on the 2-query case. Actually, we're going to start with the 1-query case, so we're going to be even more basic than that. But we're going to show that like the first thing we're going to try to show is why 1-query LDCs for insertions and deletions do not exist. And then we're going to start, okay, I guess that follows because they shouldn't exist in the substitution case, but like we're going to go through a slightly different proof of that. And then we're going to try to extend it to the 2-query case, and we're going to see like sort of for the differences and try to discuss the ideas to fix it. Okay, so what is a process of like performing what is a process of, so I guess let me write 1-query case. What does the process of performing a query look like? So you have some index I. This is an index of x. xi is an x. Your goal is to recover it. So what do? You ask like, you query some index j in the encoded word. But because there are insertions and deletion errors, what you actually get is the index j hat. I guess we cannot think too much about the insertions. Like maybe j hat isn't quite a real index in the original word, but it's really not that important because, for example, these results hold if you just have deletion errors and not insertion errors. So j hat is the index of y that you actually get when you attempt to query j, like in the Hadamard example there. When you queried y5 instead of getting, when you queried y6 instead of getting y6, you got like y5 or y7 with some probability. So j hat is the index, or sometimes we'll think of it as the distribution of indices that you actually get when you make the query to yj. And then at the end of the day, this gives you an output in 0, 1. So does this like, yeah?
Sorry, when you say probability, is that over like the coin tosses of the algorithm, or are you also assuming that errors are introduced randomly?
Right. So this, I guess, this is the decoder, and this I just mean over the adversaries. So maybe like the way to think, this is a good point. The way to think about it is the adversary has the way to think about it is the adversary has some distribution that they're using to generate the errors, and then. So yeah, the adversary has some distribution that they're using to generate errors, and that distribution tells you, given a query to the index j, where does it actually land? Where does it actually land in the code word y? So does this like flowchart make sense then? Okay, cool. Yeah, so I guess really the question, as people have pointed out so far, the question is like, how big is the range in which j hat can land, right? Like if it can be really far away from, really far away from j, and you have no predictability over this, then that might tell us that you really can't get much information about the index I in this process. Let's formalize that intuition a little bit. So okay, I guess let's start with like a silly approach. So the silly approach would be that the adversary strategy is to delete each bit with like some small probability, like probability epsilon, independently at random. Then what does j hat look like? So adversary, delete, then essentially j hat is going to be j plus minus root j, right? If every bit gets deleted with like some constant probability. So the problem with this is that actually in this case the encoder has an encoding that'll recover. In this case, the encoder has an encoding that'll recover j hat just fine, or sorry, will recover like xi. And the encoding is really simple. It's just the repetition code. The encoder encodes x1 many times and then x2 many times, all the way to xn many times. And the thing is, if they query an index in the middle of this block, like if they query an index in the middle of the x2 block, then since the unpredictability of it is only plus minus root j, which is bounded at plus minus root m, we can say that the length of the code word is m. Then as long as this block is long enough, they're very, very likely to get an index that actually falls within the x2, and they actually can recover like xi. Does that like make sense? Yeah, so that's not a good strategy, but there is another really simple strategy that works. The other really simple strategy is choose a random number between 0 and epsilon n and delete that fraction of the bits. If you do that, then instead of getting j plus minus root j, you're going to get j plus minus epsilon n, or what j hat actually is. And then in that case, we have our encoded word y1, ym. And essentially we can, the unpredictability of where a specific index j lies is very large. Like it's like about epsilon n. And what that means is basically like if you perform two queries that are very, very close to each other, if you perform any two queries that sort of land within the same bucket, then the distribution of what j hat looks like in both cases is actually basically the same. So you can divide your range 1 through m into a constant number of buckets, such that if you query j from the same bucket, so divide So you can divide your range into a constant number of buckets, such that if you query J from the same, any queries of like J from the same bucket will result in approximately the same distribution of J hat. Does that make sense? Like you want these ranges maybe to be a little bit smaller than 1 over epsilon, or like, sorry, a little bit smaller than epsilon n in size, and then this will basically end up being true. Does that make sense? Okay, cool.
Can you actually explain what are you assuming and what did you get?
Wait, sorry, can you clarify the question?
So you assume some error model where the adversary erases some number of bits in the beginning?
Yeah, so
You're doing something which I didn't quite get.
Okay, so the error model here, like this step, the adversary erasing, in this step, the adversary is erasing some bits, and that's going to result in a J hat that's like not exactly equal to the J, right? So the error model that they're going to do is they're going to take a uniformly random number between 0 and epsilon n, where epsilon is the allotted fraction of corruption, and then they're going to delete that many bits from the beginning. So basically what that does is it'll shift the index J by a little bit, right? And the question is, how much is it going to shift the index by? It's going to shift it some random number between 0 and epsilon n. And what that means is if there are two indices like right next to each other, like J and J plus 1, then the distribution of the output indices is basically the same, right? And in fact, as long as the two indices, J and J prime, were within like, epsilon squared n of each other, let's say, then this distribution will be then the distribution of J hat will be basically the same. And if the distribution of J hat is basically the same, then the distribution of the output of 0 and 1 is basically the same. So that's why you're not going to be able to extract information any different if you query two J's in the same like small range. Yeah, so the point is there's only a constant number of these small ranges, and you're trying to recover a super constant number of indices I, so you aren't going to be able to recover that much information. Does that like vaguely make sense? Okay. Yeah, so I guess the first thing we might try to do in the two query case is reconstruct this argument. So in the two query case, what does the diagram look like? We have an index I. We have two indices, J1 and J2, that we query. And then we have two indices, J1 hat and J2 hat, that are the actual indices you end up querying. And then the actual output is going to be in 0, 1 squared. Right, so what we would want, I guess in this case, essentially the like key step here was that J hat could be like J plus minus epsilon n, right? So what we would want is the same thing. We would want that J1 equals J1 plus minus epsilon n, and J2 equals J2, or J1 hat, and J2 hat equals J2 plus minus epsilon n. When I say plus minus, I just mean within that range, like sort of uniformly. But really it's not uniform, but it's not super important. Anyway, so this kind of isn't actually possible because J1, sure, like independently J1 and J2 will be will satisfy this distribution, but we care about like the joint distribution of J1 and J2. Like we care about what they are combined. And it turns out that if J1 is larger than than expectation, then J2 is also probably going to be larger than expectation. And in fact, like if you do that exact deletion pattern where you just delete like the first chunk of indices, then what you're going to get here is that deletion pattern from before. What you're going to get here is J2 hat equals J1 hat plus J2 minus J1. Like the difference between them is not actually going to change because you're only deleting stuff at the beginning. And actually, like this is going to be enough to this would actually make a Hadamard code work, right? Because in the Hadamard code, all you care about is the difference between the indices anyway. So this actually so the same deletion pattern doesn't work, but like you also might not expect it to work because it's a really silly deletion pattern. So I guess maybe the next goal we might hope for is the thing we can actually get is we can get a distribution. We can have the adversary perform deletions in such a way such that J1 hat looks like roughly J1 plus minus epsilon n, and J2 hat looks like whatever you got for J1 hat plus minus epsilon times the difference between the two queries. So that, it turns out, is a deletion process you can do. I will note that this deletion process, that being able to get this actually doesn't extend to like large constantly many queries. It turns out that you can do this for 2, but you actually like won't be able to do it infinitely. But anyway, even but let's say like even if you can, but this deletion process does exist for 2 queries, and we're just focusing on 2 queries. So the argument we used before was that basically like in the 1 query case, the argument we used was you know, if the distribution, if 2 indices have if 2 possible values of J and J prime have the property that J hat has roughly the same distribution, then they're only going to be able to tell you information about the same constant number of indices. They can't tell you information about different indices, right? Or at least not about too many different indices. So we would like to be able to do that, to generate something like that here. Like in a sense, we are bucketing our possible queries into buckets that like generate the same information, right? Unfortunately, we can't actually do that here. And maybe that isn't super clear from the formula, but let me try to explain why. So I guess look at the following queries. J1 comma J1 plus 2. Oh, okay. Yeah, it's not visible, right? Oh, okay, cool. That's great. J1. Yeah, I don't know. I guess I could go there, but then there's like a disconnect. Okay. Yeah. Let me redraw a little bit of this then. So we have like I, 2. And we are able to get, we're assuming that we're able to get the property, which is sort of the best we could hope for, that J1 hat equals J1 plus minus epsilon n. Okay, so now we sort of like want to do the same thing as before, where we are able to bucket all pairs of queries into about a constant number of pairs, where the distribution of like J1 hat and J2 hat will be basically the same, right? But like, it turns out that you actually can't do this. If you just like look at queries that has like exponentially increasing differences. If you look at these pairs of queries, like even though J1 hat will sort of be the same, have the same distribution for all of these, the conditional distribution of J2 hat will be different for all of these queries, right? So the number of buckets of queries that like we wanted to look that like essentially look the same is actually like, you know, super constant. In fact, there's the amount of such buckets we're going to get is going to be log m, because the number of buckets can be as big as like the length of the encoded word. M was the length of the encoded word in this situation. And this actually like leads to the exponential lower bound that was shown in the FOCS 2021 work. And basically like all of the, like basically the idea is that all the queries that sort of look like this are all going to be able to only give information about the same constant set of indices. All the queries that look like this are going to be the same. All of these queries are going to be the same, and so on. And all of those, basically all the queries in this group are all going to give the same distribution of J1 hat and J2 hat, and therefore have the same distribution on outputs. So unfortunately, this doesn't prove like a non-existence result altogether, right? Like this, like there are actually a super constant many of these, and therefore like you could in theory be able to make all of these distributions have different outputs. And if all of these distributions had like sort of, if you could set the distribution of all of these outputs like separately, then you would actually be able to get a LDC for insertions and deletions. So the main idea that lets us go past the exponential lower bound is, and prove that they don't exist altogether, is to show that actually a lot of these distributions, even though they have a lot of these pairs of queries, even though they have different distributions on these, will actually have the same distribution on this. So the basic idea is that you can group these queries into a constant number of chunks like this, and even though they'll have a different even though like the queries, the two pairs of queries listed here are going to have a different distribution on J1 hat and J2 hat, they'll have the same distribution on 0, 1 squared. Because at the end of the day, you don't get to figure out what J1 hat and J2 hat are. You only get to figure out whether the outputs were 0 or 1. Does the like vague claim make sense? So I think I won't actually be able to get into the proof of this claim because I don't think I have enough time for that. But I just sort of wanted to like sort of boil down the problem, say like what the general approach to proving that these don't exist are, and say like sort of what the point at which we need to do something. We need to do something where we don't just exploit the queries themselves, but actually the outputs is.
Continuing King's question, for like log and alphabet size, this could be a problem. Like, to do that?
Yeah. I think log and alphabet size, it would start to actually be a problem because this really only gives this method really only gives a lower bound against constant query. I have no idea whether they should or shouldn't exist. I would guess they don't exist for log n size, and I'm going to get into that and actually maybe in a second. Okay, let me see how much time I have left. Okay, I think this is probably a good time to talk about concluding remarks, and like open questions that remain in this area. Okay, so the main theorem that we said for this talk was that constant query locally decodable codes for insertions and deletions do not exist, right? I think one of the most interesting open questions is how many queries do you need? So the work of OPC 15 showed that like you can get polylog query insertion, deletion, LDCs. But one thing to note about their construction is that like it's adaptive. Like you don't specify all your queries beforehand. You actually like make your queries in sequence based on the previous results. And this is actually very important because essentially they're just binary searching for like the index in a substitution LDC.
So this one gives better query complexity than a standard LDC?
No, it'll be a log factor worse than a standard LDC. Because it's basically a substitution LDC, but they on top of that they binary, like when you're trying to query the index xj, you don't know where the index xj is at, or yj, you don't know where that actually is in the code word, so you do some binary searching to find it.
It's not constant rate and constant distance. Yeah, it is constant. You can take a read molar and just transform it into an insertion deletion. It's a concatenation between Schulman-Zuckerman and the code itself.
We don't have
Actually, I think we don't have constant rate.
And you can simulate Hamming errors with instead errors.
I think this is actually not constant rate then.
Yeah,
So it's not constant rate. Okay.
Yeah. This shouldn't be constant rate.
Okay.
Yeah. I'm sorry. I forgot the results.
Because otherwise you
I
get
think the best query complexity we have is 2 to the square root log n if you want constant rate, constant distance.
Okay, it's larger.
Yeah.
Otherwise, yeah.
Yeah, so I think this will be like slightly super constant. Great. So I guess the most interesting question is how many queries do you need? So this one is like, you know, in the like adaptive setting, you can get polylog n queries. But I think specifically this question is interesting in the non-adaptive. Because there's no better result than just n. Like there's no better result than just you have to query the entire code word. And I actually think it's possible that's tight. I have no idea. So I think that's a really cool question. Let me see what else I had written down.
Well, I mean, you never have to read more than, like, okay, maybe like 1 minus some epsilon n because of just for.
Yeah, let me add a theta here, or like a omega. Yeah, I guess the second question is, so the deletion pattern that results in this process is pretty simple. And the deletion pattern that's used to go beyond 2 queries and like show that k queries is impossible is actually like very complicated. And essentially, it isn't even able to get a claim that looks exactly like this. Like you aren't really able to induct on this claim. And I think there's actually a proof that that's impossible. But you can get something that's close enough for the purposes you need. But I actually believe that it's possible that with this deletion pattern alone, the deletion pattern that achieves this, it might be possible to show an impossibility result for k queries. I don't know if that's true. So I guess maybe more broadly, can we use a simple deletion pattern to achieve this impossibility result using like a clever argument? And just in general, can we simplify the proof? Because I think simplifying the proof and like really extracting the info-theoretic parts that are necessary will also help make progress towards this question. Because I think right now the proof is a bit jumbled and it's kind of hard to, like, I guess beyond the idea that I haven't stated but will work for here, the extensions are all just like very clunky, and extending it to k queries is really just not a very nice argument. And I think if we simplify that, we might be able to extract why the answer is actually like omega of n, or at least I think it might be omega of n, or extract why that's not true. Yeah, so I think this is probably the most interesting question, and this one I think will help lead to an answer here if we can make simplifications to the proof. Yeah, I think that's basically what I wanted to say. Thank you.
Questions?
Yeah.
So what alphabet do you need so that it will be possible to have constant query LDCs? For example, if you have exponential set alphabet, will it be possible to make?
I mean, if you have an exponential alphabet, then in a single symbol, you can encode the entire word, right?
No, because like your message also will be like exponential.
Oh, I see. I think this conjecture would imply like no alphabet should work, right?
Yeah. Okay.
I think my proof will only imply that constant alphabet won't work. I don't think my proof will tell you that anything beyond constant alphabet will work.
Do you know like if you have like random noise? Because like usually like for regular LDCs, random noise is very easy. But here it doesn't seem that random noise is very easy. Doesn't like your lower bound imply that for say completely random noise it's impossible to have constant LDCs, or?
So I think with independently random noise, you do get LDCs, and the reason is really simple. It's just this argument, which is just like you can take your message and you can repeat like every xi many times, and then if you query like the middle of the range, then the bit you get back, like even with only one query, if you query the middle of the range.
Huh? Constant rate.
Oh, constant rate. That's a good question. I have no idea if you can do it with constant rate. I suspect you probably can't, but I'm not sure. I guess one thing to remark about these this impossibility result is that it holds against oblivious deletions as well. Like nothing in the argument we said really looked at what the code word was. We were just kind of trying to shift around the indices J1 and J2 as much as we could. And nothing in any of the arguments cares about what they actually were. So it does work against oblivious, but it's a good question, actually. I like that question. Can you do constant rate insertion deletion LDCs against like independently random errors?
Any questions? If not, let's thank Meghal again.